Hello folks, and welcome to this video on resistance networks. We're going to look at 4 different combinations of resistors today. And in doing so, I'm assuming that we've done some basics all about a combination of resistors in series and parallel. If you have not done that yet, I suggest you go back and watch the explainer on that, which is somewhere on my channel. So yeah, let's get to it. We're going to look at these 4 combinations, and we'll begin with a simple one, which is combination A, and this is resistors in series. Now, I should say at this stage, I'm going to assume that each of my resistors is identical in this case, and they each have the resistance capital R. Now, in combining resistors in series, we should be aware that when we take 2 resistors and combine them in series, then we simply get a bigger resistance. The resistances add together, and so therefore, in this case, we're going to say resistance A, the total resistance of combination A, or effective resistance, sometimes it's known as, is going to be RA is equal to simply to R plus R, and that's 2R. All right. This is similar to when we make a resistance wire longer. We make a longer resistance wire, we're therefore making a greater resistance. So that's our first combination. Shouldn't have been too tricky. The next one is obviously to simply go and have a look at what happens when we combine in parallel. Well, parallel is slightly harder. What we have to do is remember our rule of reciprocals. So in this case, we've got combination B. We should be aware that 1 over RB, it's the effective resistance in B, is 1 over the individual resistances added together. And again, we're assuming they're identical. So we've got 1 over R plus 1 over R equal to 2 over R. And again, this is where we just need to remember what we're doing. We're trying to calculate the resistance, not 1 over the resistance. So we need to remember our final step, which is to invert the values. So therefore, RB is R over 2. Okay, we just take a second to pause here. What we're saying here is when we combine resistors in series, we get a larger resistance. And when we get resistors in parallel, we get a smaller resistance. And when they're identical, we actually get double the resistance in series, and we get half when we're combining in parallel. Okay, so much for the sort of basic ones. Now what we want to do is introduce a third resistor and see how that changes things. Now, we'll see here combination C. This is now a mixture of series and parallel. You can see that on the top branch there, we've got a series combination, and on the bottom branch, we've got a resistor connected in parallel. Now, this is where I find that students don't really know what to do next, because we've got a mixture and there's no specific formula for this. Well, the thing to do is to treat the multiple resistors first. So in this red box, we've got our 2 resistors together. Now, instead of having 2 resistors there, we could imagine, well, what would happen if we had simply 1 resistor there with the same resistance as those 2 resistors? Well, that is simply just combination A. Okay, we've already seen that combination A has a resistance 2R, and so therefore our 2 resistors on the top line there are also going to have resistance 2R. Okay, we then have a parallel combination of 2R on the top and 1R on the bottom, and this is how we're going to write it down. Okay, we've got 1 over RC, so that is the parallel combinations, is simply 1 over RA, that's our top line in red, plus 1 over R, which is the bottom line. Well, we know that resistance on that top line is 2R. We have 2 resistors in parallel together. In series together, and therefore 2R. And so therefore 1 over 2R plus 1 over R, that's the bottom line, and we end up with, if I've done my maths correctly, 3 over 2R. Again, we need to remember to flip. We get RC is equal to 2R over 3. So just take a second to work out what we've done there. Just to repeat, we've treated that top line as a series combination. We know the resistances are identical, so their total resistance is 2R, and then we can calculate the total resistance of that parallel combination. Okay, let's have a look at combination D now. Similar there. However, this time we've got a series combination of 1 resistor and 2 parallel connected resistors. This is one where I want you to have a think. Maybe pause the video at this stage and think about how you might do this one, because the process is very similar to combination C. If you're carrying on watching, I'm assuming that you've either had a go or just have no idea. Okay, what we need to do is have a look at the first this box here. We want to replace any multiples so that they are kind of simplified in the circuit. We've got a parallel combination of two resistors here, and that is simply just combination B. Okay, this is half of the resistance. So when we look at the circuit, combination D is simply one resistor R, which is added together with two in parallel. Those two in parallel, well, they've added together to make R over 2, and therefore our total resistance becomes 3R over 2. So there you have 4 different combinations of resistors and 4 processes for how to work them. Now, when you get to these complicated ones, remember the step there is to reduce the complexity by replacing those resistors with another one of the same effective resistance and then going from there. Okay, do take time to think about that, and if you've got any questions, feel free to let me know.